Thank you so much, Daniel, for the kind introduction. Very good afternoon, everyone. It feels amazing to be here. I flew all the way from India to be here with you to discuss something I'm passionate about it. Today, I'm going to talk about concurrency. Yeah, it can feel scary, but I try to make it easier for you too. We are going to explore not just how Swift concurrency works, but why Apple made such design choices and when you should use different patterns in your own projects. By the end of this session, you will have a practical knowledge and that you can apply for Swift 6 migration. Let me share a bit about myself. I'm Kanaga Sabhabati Rajkumar, and you can call me Sabha. I'm a Apple platforms developer since 2014, since like 12 years ago. My passion lies in concurrency and Swift package management, which can shape your app's architecture. I'm also a co-organizer to Swift Bengaluru, a local iOS community meet. And also I host Swift Published Talks podcast, where I speak about Swift iOS development and of course AI development. Now you know a bit about me. So let me help you to understand why this talk is valuable to you. If you're migrating to Swift 6, and you might have seen sendable errors, and you know how to handle sendable errors, unsure when to use the main actor. If you care about Swift 6.2, approachable concurrency features, then perfect, this talk is for you. Or maybe you just want the practical patterns you can use immediately. This talk is for you. Sound familiar? Great, let's dive in. Before we dive in, let me ask you a question. How do you handle non-sendable types in your concurrency model? Any guesses? So this is a classic example of non-sendable that produces the data race. To resolve this, we wrap them into an actor. It's implicit sendable and mutable and safe. Otherwise, you use this unchecked sendable, and we can promise it's safe to the compiler. Here's the other one. What are the implications of using main actor? This is the question we see constantly on the Swift forums. Teams migrate to Swift 6, and we mark everything with the main actor annotations to make the errors go away, and then wonder why their app performance degrades. Here you can see this left side, in the left side you can see this JSON parsing and also fetch API from remote that can block your UI code, UI thread, and in the right side you can see this. We have used the async await that creates a potentially context switch and a suspension point so that it can freely fetch the data from background. Let's recap about the concurrency journey. Swift 5, we have got async await, actors, and structured concurrency. We got really excited. Finally, a modern Swift concurrency. But the reality hit in Swift 6, we got the complete concurrency checking. And the migration path was too steep. There are so many errors. We had a sendable or main actor. In 2025, we got approachable concurrency. It's a practical adaptation. We have gone from this is great to this is impossible, and now this actually works. We have a code base before Swift 6, zero errors, everything compiles, life was good. When you flip the switch to Swift 6 language mode, you got so many errors. Let me break down what actually happened. If you see the sendable, those were the warnings. Now we got errors and won't compile anymore. In terms of isolation, before actors were optional. Now you must specify where your code runs. On an actor or a main actor. You have to be explicit. So from 9 warnings and now we have 1,000, 2,000 errors, and mostly sendables or main actor. This wasn't a migration. This was just a rewrite. So why Apple do this? Why they break everyone's code? Before I answer, I just wanted to tell you some concept called trilemma in software engineering. You can achieve 2 out of the 3 goals. Source compatibility, the existing code will work, no issues. Complete safety, the compiler check the data races. And 3, the incremental migration, you can able to migrate the code from one version to another version, module by module, and of course, feature by feature. Here's the problem, you have to pick only 2. Let me show you what Apple chose at each stage. Swift 5.5 chose source compatibility and incremental migration. So Apple wanted your existing code to work so that we can adapt the async await in our code. So what did they sacrifice here? Safety. Sendable warnings are just warnings, but we ignored them. In the results, warnings you could ignore, you got the unsafe code. This was the right choice for the adoption. In terms of Swift 6, they chose complete safety and incremental migration. In this case, data race has to be get in the compiler. That's the whole point of the concurrency model. Migration is also important. What did they sacrifice here? Source compatibility. So many breaking changes. Apple made the hard choice, safety over the compatibility. And the community feedback was intense. Teams were struggling to migrate. This is what we led to Swift 6.2 approachable concurrency, and now they listened us. This was the turning point on March 25, the approachability initiative. The goal was simple, to make Swift concurrency approachable. This came directly from the community feedback, from those developers posting, I have so many errors, 1,000, 2,000 errors, where do I start? Swift 6.2, that reduces the friction and providing the better defaults and making the incremental migration module by module. Here are the 5 key proposals that make Swift 6.2 approachable. You can scan the QR code to check out the proposals we have got in the Swift 6.2. 0461 async functions inherit isolation. This is huge. We can discuss later. And it's everything about how async function work. Isolated protocol conformances. Finally, protocols can work with the actor isolation. A task immediate for the synchronous context. Task naming is better for debugging the concurrent code. Task priority escalation that prevents the inversion issues. They are not isolated features, they are cohesive system for making the approachable concurrency. But in Swift 6.2, all complexity goes away. You can enable the approachable concurrency even in the Swift package manager. We need to add these 2 compiler flags non-isolated, non-sending by default, and infer isolated conformances. Here's something interesting. You can actually use this approachable concurrency in Swift 5 also. But you need to add 3 more compiler flags. So each feature controls a specific behavior. You have to understand before you adding it. If you're curious or need those features in Swift 5, this is how you can enable them. This is the actual build setting in Xcode 26. One checkbox, approachable concurrency. You don't need to remember the flags I have added in the previous slide. All 5 compiler flags are all the right defaults. This is what approachable means. This tool does the work for you. There is another critical, crucial build setting, default actor isolation. So main actor and non-isolated. Non-isolated, we all know that code runs wherever, no actor isolation. This was the Swift 6 default. Main actor, that code defaults to running in the main thread. This is what most iOS applications actually want. For the heavy UI applications, setting this to main actor, it means your view and model and properties and methods is main actor by default. Before Swift 6.2, we had to use the main actor everywhere. Like I said, view model, and properties and methods. After this proposal, and also we had discussed about the build setting, we don't need to use the main actor annotation anymore. The compiler does the work for you. Let's clarify the 2 keywords that can confuse everyone. Sendable closure and sending. They sound similar, but they are completely different concepts. Sendable, the type can be shared safely. Sending, the value is moving permanently. So we will see this example. UIKit types are non-sendable. Similarly, UI image is part of UIKit and not sendable. So we got the issue, it can't be captured in the sendable closure. So how can we fix? With the sending, the compiler allows it because we have transferred the ownership. Adding the sending before the UI image, and the compiler succeeds. But after the task blocks, you can't use the image anymore. So this is a trade-off. The sending lets you to work with the non-sendable types, but you give up the access to them. So this is a decision tree. If you want to pass a value across the isolation boundaries, if it is a thread safe, and you can go with the sendable protocol. If it is a closure or a function type, you go with the sendable closure. And if you want to transfer the ownership, you can use the sending keyword. If not, you can redesign or use unchecked sendable, but be careful before doing this. Now let's talk about sendable metatype. This is new in Swift 6.2. It's a part of SE0470. This protocol exists to solve a very specific problem in isolated conformances. Before we see the solution, let's discuss about the problem here. Here, my model type is main actor isolated that conforms to the equitable. And we have got the compiler error here. My model type is main actor isolated, but equitable expects a non-isolated methods. Here, in this double equal to from the equitable method, that causes the issue. So, the 2 different isolation domains that don't match. Before 6.2, we had a workaround non-isolated. We marked the function as a non-isolated. And you can add a assume isolated to accept this double equal to. But when you have a main actor isolated, you have placed the non-isolated, then it's not useful for main actor in the first place. So here is the solution in 6.2. So we can add the main actor to the equitable protocol explicitly. And now the one issue has been resolved here. The problem was main actor class could not conform to the equitable. The solution, sendable metatype that bridges the gap. Here is the actual definition of the sendable metatype. It's an empty protocol, and you can see the sendable that inherits from the sendable metatype. The answer is about the metatypes, the type of a type. MyModel.type, if MyModel.type is a sendable, then this enables the isolated conformances. Now, main actor class conform to the sendable protocols if its metatype is a sendable. It's subtle, but it makes protocols work with the actor isolation. Now let's talk about another proposal, AC0461, async function caller isolation. It's a game changer in the Swift 6.2 approachable concurrency. It fundamentally changes how the async functions work. Before this proposal, when you call an async function, the compiler assumes that it might hop to the background thread. So every await is potentially a context switch. After this proposal, async functions will inherit the caller's actor by default. If you call an async function from a main actor isolated, it stays on the main actor. Why is the game changing? No more accidental thread hops and better performance with the fewer context switches. Let me show you the problem. We have a view model that is a main actor isolated, and the refresh content is an UI code. The task is a non-isolated. Inside the task, we have a load remote data with the await keyword, and that might hop off the main actor. And you don't know whether apply data to UI will run on the main thread. So it's not guaranteed to run on the main actor. So eventually you will get the crashes or UI glitches. So this pattern is everywhere in all code bases. It looks safe, but it's not. Before this proposal, we had to fix manually. So this is a visualization of this problem. After the task, and it goes to the background thread, and it hops off to the background thread. And when you hop back to the main actor, this is how. Before that, we can see the workarounds we had earlier in this Swift 6 and 6.1. So any guesses? So we had UI code and also load remote data. So I'll tell you. For wrapping the UI code, we had a MainActor.run followed by the closure. So you can explicitly jump back to the main thread. And marking the non-isolated function for the loading the remote data. In other ways, you can go with the actor, wrapping into the actor and loading the remote data. But now crossing actor boundaries adds an overhead here. All these work, but when it get messy when in the large code bases. SE0461 that makes this unnecessary one. Now you can check this. This is a problem, and you can see the solution in Swift 6.2. The same code works well with this Swift 6.2 approachable concurrency. Now you can see the non-isolated function that will call the actor, call as actor. So the view model is main actor isolated. So this function will run on the main actor. Previously, it will run on the background. And applying the data to UI is easy and safe access. So all will remain on the main actor. So this is non-isolated async functions now can run the scholar's actor by default. This is the tagline. The correct behavior is now the default behavior. This is just a flow. You can see with Swift 6.2. And it inherits the main actor from caller, the non-isolated function. And coming back to the view model, and there is a no actor hopping to the background thread. Everything runs on the main actor. Look at this image, everyone pulling on the same rope at the same time. This is exactly happens when 100 tasks try to use the main actor simultaneously. They are competing for the same single-threaded resource. They are pulling on the same rope. Main actor can execute only one at a time. It's a serialized one. They queue up and they just wait and our UI freezes. The solution, we have a concurrent attribute here. This is brand new in Swift 6.2. This is how you can explicitly say that this function should run concurrently in the background. Think of something similar we had in GCD, dispatch queue.global. You are opting into the background thread. These are the operations you don't want to add it in the main thread. Even it's called from the main actor context. Concurrent is your explicit opt-in for the background processing. When you call from the main actor code, the compiler automatically inserts a context switch for you. You don't need to write anything. This is the flip side of this SE0461. The plain async function inherits the caller's isolation that stay on the main actor. Concurrent functions always run in the background, explicitly opt-in. We all know this default modifier. So default function with no modifier that runs on the actor's isolation. We have a non-isolated. In Swift 6, we have two methods. One is async and non-async. You can add the non-isolated to the functions. The same keyword, two different behaviors we have seen in the Swift 6. This runs on the caller's actor, the first method, and the second method in Swift 6 that runs on the background. Now in Swift 6.2, it runs on the caller's actor isolation. We have a non-isolated non-sending that runs on the caller's isolation. The keyword non-sending means I'm not sending across the isolation boundaries. I stay with the caller that runs on the caller's isolation. Sending would mean the transferring across the isolation boundaries. Non-sending, non-crossing the boundaries can use for the non-sendable types. Unlike non-isolated, you can use for the async here. So concurrent we have already explored that runs this function on the background thread. The real world examples you can use for JSON parsing of large data sets, image compression, or a PDF generation. This is just a flow chart. If it is a non-async, you can go with the non-isolated. And now non-isolated will run on the caller's isolation, or non-isolated non-sending that runs on the caller's isolation. Concurrent that explicitly run on the background. So this table is crucial. We have approachable concurrency and also default actor isolation. So we have three different methods: normal async function and non-isolated async function, and we have a concurrent async function. When you set no for the approachable concurrency and default actor isolation is main actor, the first function will run on the main thread. And if you make as a non-isolated for the default actor isolation, it will run on the background thread. When you set S to the approachable concurrency and you have a main actor, the normal async function and the non-isolated async function will run on the main thread. Similarly, when you set to the non-isolated, still it will run on the main thread. So the key insight is when approachable concurrency is set on, the plain async function and non-isolated async function inherit their caller's isolation. So this is a magic. So we have other choice for networking. We can't depend on the concurrent anymore for large code bases or when you retrieve large amount of data from server or when you depend on this. So we can go with the non-isolated default actor isolation. Non-isolated means the code runs wherever, no actor isolation. So everything I have shown you so far is true and helpful. SC0461 is a great feature, but there is a cost need to discuss honestly. It's a kind of thing that doesn't show up on the demos or a post. So it shows up in our production code, especially in the large code bases. Let me show you the flow. In Swift 6, without this proposal, it runs in the background and comes back to the main actor. But if you see the Swift 6.2, it blocks the UI code. It stays on the same main actor. So here is a better version. You can see we have a task group that runs on the parallelly. But when you add it in the main actor isolated, and you have a fetch one that is a main actor isolated method. So here is a single thread source, and you are running 100 tasks at a time. So this causes the UI issue, and you are changing the behavior of the task group to serial. Here is how we can fix it. We can add the concurrent attribute before the fetch one method, and this will run in the background. Now the task group will run on the parallelly on the concurrent thread pool. So mark your network or heavy work as a concurrent. Let task group run parallelly. This is the pattern you need to internalize in the Swift 6.2. Now let's talk about the bug that has nothing to do with the Swift 6.2. Look at this method. We have a balance, and we are checking in the step line number 4, and also we are calling the await. We might call the withdraw function again in the line number 6 that creates a context switch. So, and then we are updating the balance here. So balance might go negative. In this case, we need to capture the state before await, and we can have a new balance here. And later you can assign the captured value after the await, after the suspension point. So this pattern works for all actor reentrancy scenarios. Capture the state before await, do async work, and use the captured state after await. Let's talk about another common pitfall, ignoring the cooperative cancellation. The Swift concurrency model uses the cooperative cancellation. That means the system can request that a task can cancel. But the task has to check and cooperate. The cancellation is not forced. If your task never checks for the cancellation, it will run forever. Even when the user navigates away or the app is terminating. This is the production bug we see constantly. The long-running task groups can't be stopped. So let me show you the problem. The same code we had discussed earlier with the concurrent introduction. So we are adding the task.check cancellation. So by checking the task.is cancelled or use the try task.check cancellation in your loops. So this demonstrates the Swift's cooperative cancellation model. It only works if you cooperate. SC0469, the task naming. This is a huge quality of life improvement for the debugging. Before that, all the tasks were anonymous and in the debugger and also instruments. It's very tough to identify which task is which. After this, you can name the task and also along with the context, especially image ID or a data ID, so that you can easily capture those things. So you can see these in the thread list or Swift concurrency instruments. And of course, you can see where the task has crashed, the crash logs, and OS log messages. So this makes the debugging concurrent code so much easier. You can actually see where is running and which task is running. So this is an example I have tried with the few task namings, And in this running task, you can see the task naming with priorities and fetch user profile and nested name task. So we can see the average duration and minimum duration maximum. And while ending, you can also check these same task, the closure. So let's wrap up with the narrative arc we have been following. In 5.5, we built it and we got so many warnings, but we ignore and we replace with the manual annotation. In the result, optional safety is not a real safety. In 6.0, too strict, and we got thousands of errors while migration. We annotated with the workarounds. The result, complete safety, but painful adaptation. Act 3, we have is 6.2, it's approachable concurrency. The correct path is now easier path. Features are like smarter defaults, inference, and main actor by default. Now it's safety and usability. So classic 3-act structure introduce the concept called concurrency, make it too strict, the struggle, and the find the resolution with the balance. We are now in the Act 3. Swift concurrency is finally approachable. Let's take a quick peek of Swift 6.3 and beyond. We are getting the weak-let. We were using weak-var. Now this helps with the sendability checking. And you can add the async await inside the differ bodies. We have discussed about the build setting with the default actor isolation. Now we can enable the default isolation in the file also. And you can experiment with the experiment feature flag default isolation type alias. The approachable journey continues. Let's stay tuned. Let's recap the key takeaways. Start on the main actor, set as a default for your iOS applications, and use concurrent for the explicit background task and sending for the ownership transfer. And it works well with the non-sendable types. And capture the state before await for the actor reentrancy issue fix. And check cancellation liberally. So the compiler is your friend. Trust the errors. They are catching the real bugs. And remember Swift 6 that prevents the data races, not the race conditions. You still need to think. Here's the good news that Swift 6 to 6.2 makes it approachable. The correct path is now easier path. So thank you so much for the opportunity. That's it. My socials or contact information is on the screen. Feel free to reach me out. And if you're at the conference, let's chat during breaks or tomorrow. Thank you so much for the opportunity, and thank you so much for your attention. Enjoy the rest of the conference.
Thank you. Do we have questions? Right here.
Hi, thank you for your presentation. It was quite big, so maybe I just missed it. But we talked about the problem that we had before Swift 6.2, right? When we had an await call, right? And after that, we updated our UI, so we could call the UI update on a background thread, right?
Yeah.
Is this problem fixed in Swift.2 if you call the concurrent function after that? So it just hops back onto the main thread after it finishes, right?
Yes, correct. It will run on the concurrent thread pool, so you don't need to add it. Actually, this is a fix for earlier we faced in this Swift 6.0 with the non-isolated. Now non-isolated will run on the caller's actor isolation, and concurrent will run on the parallel with the background thread.
Okay, thanks.
Thank you.
Down front.
So you mentioned a lot of problems that you can do accidentally with Swift now and the solutions to them. But let's say there's a lot of code. What, for example, would be the best instrument to check if you have these kinds of issues? For example, the 100 task one.
We can check the async hangs, and also now we can check the task also with the naming. Yeah, I think we can use the async instruments is better for debugging the concurrent code.
Okay, thanks.
In the back on the right. And while you go there, I'll ask a question, which is, you gave us this 3-act structure, Swift 5.5, Swift 6, 6.2, and then you looked ahead to 6.3. Are there things you consider pain points that we haven't addressed yet that you think they need to address with concurrency?
Yeah, there are still some pain points with the 6.2 also.
So what would you advise people? What are the things they should watch out for?
Currently, I faced with the protocols, so still it's giving a bug actually, but it's not a bug. So I think in the future they might resolve it.
Yeah, just a question. Sorry, I'm very scared to ask question.
Yeah.
About migration, will you go from Swift 5 to Swift 6, or you will skip Swift 6 straight to Swift 6.2?
Yeah, anyways, you need to add the strict concurrency for checking this, whether it's complete or targeted.
Yeah.
So you need to use this Swift 6 as well, but you can directly go with the approachable concurrency.
But what is your advice better?
Sorry?
Which one would you choose? Like,
If you see the build settings, there are 3 settings. One is approachable concurrency, and then default actor isolation, and then strict concurrency checking. So anyways, you need to use Swift 6 and 6.2. So you don't need to.
possible to skip this migration from Swift.
6.2 would be better.
Okay. Thanks.
Thank you.
Thank you. Anyone else?
All the way over there.
Can you throw it there?
Try to.
Watch out in between. Well done.
It's here, right? So my question is about tests. Once you're migrated, so you have to adjust your tests. So anything you would recommend looking out for, or from your experience, any highlights regarding tests?
Yeah, in terms of the Swift testing, we have a Swift testing framework that nowadays it supports the Swift concurrency actually. So you can see the latest experts and something. The new functions that has been introduced in the Swift testing framework. I think you can start testing with this.
Anything for the good old XC test? Any comments on that? Or, yeah, if you had experience with that, of course.
No, actually.
Oh.
We need to test.
That's a good answer. Anyone else? Well, please thank Saba.
One? You're too late. One more? Can we do that?
Thank you. I want to ask about GCD and combine regarding Swift 6.2. I mean, how do they work? Do they have any conflict regarding using concurrence or main actor? I mean, if I mark my method with concurrence and I use it in GCD or combine, does it have any conflicts or issue with that?
Actually, you can combine with the Swift concurrency with GCD and also combine. It will work as expected. But my suggestion, you can go with the async sequence. That is better. I think that's a replacement for the combined framework. This is my.
Thanks.
Please thank Saba. So our next speaker, I talked to the speakers to say how they want to be introduced, and the thing she did